The Webb glance is such a long way out that it's catching light that has been voyaging for over 13 billion years. Yet, the universe has been expanding and thus the light has been stretching. For the most distant worlds, we're thinking back in time, nearly to the Big Bang. The immensity of the universe might seem vast, but every last bit of it started from what we allude to as the singularity. As of now, this is how we interpret the Big Bang hypothesis. However, the James Webb Space Telescope, JWST, has revealed significant mysteries about the birth and development of the universe, leaving us dumbfounded. Prestigious physicist Brian Cox has proclaimed that the discoveries made by the JWST might actually reshape our understanding of the universe as a whole. Join us as we dive into these new heavenly discoveries that promise to change our comprehension. The James Webb Space Telescope, named after the distinguished NASA executive James E. Webb, stands as a wonder of modern galactic investigation. This telescope represents a huge technological leap forward from its predecessor, the Hubble Space Telescope. Resulting from a collaborative effort between NASA, the European Space Agency, and the Canadian Space Agency, the JWST surpasses the abilities of its forerunner. It utilizes cutting-edge technology and a design enhanced for concentrating on the universe in remarkable detail. Unlike the Hubble, the JWST delivers clear and sharp images of far-off celestial bodies, working primarily in the infrared range. This feature allows it to penetrate cosmic dust and capture celestial objects that were previously hidden from our view. With its giant 6.5-meter primary mirror, composed of 18 hexagonal segments, the JWST vastly outshines the Hubble's reflector size. Positioned roughly 1.5 million kilometers away from Earth at the second Lagrange point, L2, it orbits the Sun in synchrony with Earth, ensuring a stable and continuous view of the universe. While looking into the far-off corners of the universe involves exploring light years, it also involves a kind of time travel. The JWST uses infrared instruments to observe celestial objects and events going back billions of years. The light emitted by these objects because of the expanding universe experiences redshift, shifting from the visible spectrum to the infrared wavelength. Fortunately, the JWST can detect infrared light emitted by celestial bodies at extreme distances, enabling researchers to study the birth of stars, explore galaxy formation, and examine exoplanet atmospheres. Its latest historic discovery involves identifying an incomprehensible mass of galaxies at the edge of the observable universe. This finding challenges the validity of current theories of cosmic evolution, prompting a reassessment of fundamental cosmological assumptions. To better understand how we arrived at this point, we should take a short journey through the history of space investigation. Early civilizations like the Greeks and Chinese laid the foundations for understanding planetary movement by observing celestial bodies. Newton's laws, established in the 17th century, provided a theoretical framework for space travel. In the mid-20th century, Edwin Hubble, an influential astronomer, made historic discoveries in cosmology and observational astronomy. His observations revealed that distant nebulae were actually separate galaxies, far beyond the Milky Way, fundamentally changing our understanding of the universe's size and expansion. Hubble's law, established by him, showed that galaxies farther away were moving away at higher rates, providing evidence for the expanding universe. The post-World War II history of space exploration marked the beginning of the space race, with the Soviet Union's Sputnik in 1957 as the first artificial satellite in orbit. Yuri Gagarin's orbital trip in 1961 and the Apollo 11 moon landing in 1969 were crucial achievements. Fast forward to 1990, when the Hubble Space Telescope was launched, providing exceptional clarity and stunning insights into the universe. The journey from ancient observations to the technological wonders of the James Webb Space Telescope showcases the constant evolution of our understanding of the cosmos. It revealed the boundlessness of space and transformed fundamental ideas in astronomy. Take the Hubble Space Telescope (HST), for instance. It captured the famous Pillars of Creation image in the Eagle Nebula, revealing a star nursery formed by massive columns of gas and dust. Another significant accomplishment was the Hubble Deep Field, capturing thousands of galaxies in a seemingly empty patch of space. The HST also explored exoplanet atmospheres, identifying elements like water and organic molecules in distant worlds, hinting at the possibility of habitable zones beyond our solar system. Following the development of the closest observed supernova, SN 1987A, it shed light on the life cycle of massive stars. These achievements cemented the HST's legacy as a cornerstone of modern cosmology, dazzling the world with its incredible discoveries. Its successor, the James Webb Space Telescope, was launched to expand on the technological advancements and lessons learned from Hubble. A model of our understanding of the universe's origin is explained today by the prevailing Big Bang theory. Around 13.8 billion years ago, the universe began as an intensely hot and dense singularity, rapidly expanding and giving rise to matter, energy, and fundamental forces. As the universe expanded, it cooled, leading to the formation of atoms, stars, galaxies, and the various structures we observe today. The Big Bang theory also explains the cosmic microwave background radiation, the abundance of light elements, and the large-scale structure of the universe. Despite being widely accepted, the Big Bang theory faced skepticism and challenges in its early days. Alternative models like the steady-state theory proposed a universe without a specific beginning. Concerns about evidence supporting the initial singularity, expansion, and observed anomalies also arose. Most of these objections were addressed over time, and a significant piece of evidence came with the detection of cosmic microwave background radiation in 1965, aligning with Big Bang predictions. Space missions like COBE and WMAP, alongside technological advancements, further supported the theory. Accurate measurements of the cosmic microwave background radiation matched strikingly well with theoretical forecasts. Enter the James Webb Space Telescope, equipped with advanced infrared instruments that can look through cosmic dust. The JWST, working primarily in the infrared range, captures the oldest light in the universe and observes objects formed shortly after the Big Bang. Its infrared capabilities allow it to focus on star-forming regions, celestial nurseries, and the formation of stars, hidden from optical telescopes, is revealed through infrared light. Infrared light, with longer wavelengths as compared to visible light, can penetrate interstellar dust, overcoming a drawback of the Hubble Space Telescope. The JWST can examine cooler objects emitting specifically in infrared, making it ideal for studying phenomena like exoplanets, brown dwarfs, and remote galaxies. As celestial bodies move away, their emitted light waves get stretched, causing a shift toward longer wavelengths, known as redshift. The JWST's infrared capabilities allow it to locate these redshifted signals, capturing light from the early universe and supplying insights into its formation and evolution. Energetic activities like black hole mergers or new starbirths mostly emit in the infrared range, further increasing the JWST's investigative abilities. The telescope can discover phenomena that would otherwise be hidden or invisible. The JWST supplements optical telescopes like Hubble by offering greater sensitivity and the potential to detect infrared radiation. This ability allows it to peer deeper into space and dig deeper into astronomical history, revealing hidden astronomical wonders and providing a more comprehensive view of the universe's development. The JWST serves as our window into the earlier phases of cosmic evolution. Lately, it discovered something so astounding that it might trigger a reconsideration of the entire cosmological model of the universe. We have detected large masses of galaxies at the very fringe of the observable universe. These ancient galaxies existed only a few 100 million years after the Big Bang, during the cosmic dawn. The perplexing element is that we're unsure how such tremendous systems formed so early within the universe's history. This discovery might lead us to reconsider our understanding of the formation and evolution of galaxies in the early universe. Analyzing early galaxies is crucial for unraveling the mysteries of cosmic origins. The JWST can provide insights into how galaxies, stars, and planetary systems arose and evolved over billions of years. These observations also contribute to broader questions about the fundamental nature of the universe, such as its composition, structure, and the forces governing its evolution. While the Hubble Space Telescope was groundbreaking for its time, it had limitations in observing the early universe. Its primary obstacle was its inability to effectively penetrate cosmic dust and detect the infrared light emitted by ancient galaxies. Older telescopes relied on visible and ultraviolet light observations, making it tough to explore the early universe where those wavelengths are absorbed or distorted by interstellar dust and gas. The James Webb Space Telescope represents a significant leap forward in observing galaxies from the universe's early stages. Unlike its predecessors, the JWST can study celestial objects that formed within a few 100 million years after the Big Bang. Using its infrared sensitivity and advanced imaging capabilities, the JWST has uncovered an abundance of ancient galaxies, providing remarkable clarity and detail in understanding the universe's evolutionary history. Initial results from JWST observations have stirred waves in established cosmological models. The specific data challenges numerous aspects of prevailing theories, prompting cosmologists to rethink fundamental principles governing cosmic evolution and structure. Discrepancies between observed data and theoretical predictions have sparked intense debates within the scientific community. JWST observations have revealed a larger number of galaxies in the early universe than predicted by existing models, suggesting a more complicated and rapid evolution process. Some observed early galaxies appear more evolved than expected, challenging traditional models predicting slower development. The discovery of an unfathomable mass of galaxies challenges the assumed distribution and arrangement of large systems, revealing a more intricate and denser cosmic web than previously thought. These observations raise captivating questions and open new avenues for further exploration. The existence of massive structures challenges early models of cosmic structure formation, prompting researchers to refine models for better explanations. Understanding how such enormous structures accumulated rapidly after the Big Bang poses a puzzle that requires an explanation consistent with the fundamental principles of cosmology. Significant disparities between the conditions of the early universe and predictions based on current models have also been discovered. These differences could suggest previously unknown physical processes, unexpected conditions, or unidentified cosmic phenomena. In simple terms, these variations have caused scientists to rethink and improve our models of the universe. Currently, all we can say is that further exploration is required to incorporate these unexpected observations into a more comprehensive understanding of the universe. Initial observations often provide thrilling glimpses into the universe, but investigations sometimes reveal differences. For example, early observations may display unique properties or arrangements within distant galaxies that, upon closer examination, reveal fluctuations in their composition, structure, or evolutionary pathways. In conclusion, extensive phenomena are incredibly complex and require careful research for us to correctly understand their true nature. Spectroscopy, a method that allows the unraveling of the properties and history of celestial objects, is an example. It involves studying the light emitted or absorbed by astronomical objects. By analyzing the properties of light, spectroscopy provides detailed information about the chemical composition, temperature, density, and motion of celestial bodies. This analysis helps us understand the origins, development, and contributions of celestial bodies to the cosmic tapestry. The JWST has uncovered several instances where initial observations differed from later investigations. For example, initial observations of distant galaxies suggested a simple structure, largely dominated by lighter elements like hydrogen and helium, consistent with theoretical expectations. However, spectroscopic analysis using the JWST revealed fascinating variations in elemental signatures, identifying heavier elements or compounds previously undetected or misunderstood in the early universe. This challenges traditional ideas about the early universe's chemical composition and the mechanisms responsible for their development and dispersion across vast distances. Furthermore, initial assumptions about galaxies in the early universe were based on observations suggesting a relatively uniform pattern of growth and organization. However, more detailed investigations by the JWST revealed a much more diverse and complex array of chemical compositions within these galaxies. The James Webb Space Telescope continues to redefine our understanding of the cosmos by shedding light on previously hidden corners of the universe. One of its most exciting capabilities is its ability to study exoplanets in remarkable detail. By studying the atmospheres of planets orbiting distant stars, the JWST can detect essential chemical signatures such as the presence of water vapor, carbon dioxide, methane, and other organic compounds. These findings provide valuable insights into the potential habitability of exoplanets and the conditions that could support life beyond Earth. In addition to exploring distant worlds, the JWST is transforming our understanding of star formation. It can observe the birth of stars in regions where young stars are surrounded by dense clouds of gas and dust, which optical telescopes cannot penetrate. With its ability to detect infrared light, the JWST captures the faintest glimmers of these new stars as they emerge from the darkness, offering a clearer picture of the processes that lead to star and planetary system formation. By studying these regions, astronomers are gaining a deeper understanding of how stars like our Sun come into existence and evolve over time. Another remarkable aspect of the JWST's research is its ability to see into the hearts of galaxies. Black holes, especially supermassive ones, are believed to reside at the centers of most large galaxies. The JWST's advanced instruments allow scientists to observe the behavior of matter around these black holes, providing new insights into their growth, their influence on galactic evolution, and the powerful jets of energy they emit. These findings are helping astronomers piece together the story of how galaxies and their central black holes evolved together, influencing each other's growth. Moreover, the JWST discoveries are not only answering long-standing questions but also raising new ones. As it probes deeper into the history of the universe, it is uncovering phenomena that challenge current theories and models. These challenges drive the scientific community to redefine modern cosmological models and open up new avenues for research that were previously impossible. The discoveries of the JWST are not simply pushing the boundaries of what we know. They are helping to reshape the fundamental concepts of how we view the universe itself.